Okay. Okay, so today, oh, wait, sorry, rewind. I'm Casey. I'm the Chem 38 peer tutor for the College of Health and Human Sciences. And today we'll be going over specific heat, redox reactions, percent yield, and a little bit, which includes limiting reactants, and solutions, molarity, and dilution. So a little bit from both exam 1 and 2, and let's start with the specific heat equation. So the Q is the heat, and can anyone tell me what units are we usually measure heat in? You guys can unmute yourself, or you can just type it in the chat.
Isn't it like joules?
Yeah, joules. Yeah, so it can be in joules, which can also be in kilojoules. There's also one more type that is
Calories?
Yep, calories, and also kcals, and the big calories with the capital C. Okay, so do you remember what the K in the front means? What prefix that signifies, like what numerical value? 1,000, yeah, perfect, yeah. So 1,000 joules equals 1 kilojoule. Yes, this is for heat, yeah. This is for Q, right here. Okay, so in the same way, it's 1,000 calories, like small ones, for 1 kcal. And I'm gonna move this real quick. And it's also 1 big calorie. Okay, any questions on the unit conversions for this, or conversion factors? Okay, so does anyone want to tell me what the M in the equation stands for? Mass, yeah, and mass is usually, what do we want it to usually be in? Grams, perfect, grams. Okay, and then what does the C stand for? Specific heat, yeah, perfect. Specific heats are dependent on what substance it is. You typically in this class, you'll most likely just run into water, and it's always given to you in the problem. And then the final part is this delta T, which, can anyone tell me what that means?
Change in temperature?
Yeah, change in temperature, perfect. So it's gonna be the final temperature, oops. Give me a second. Oh no. Okay, TF minus TI. Okay, and that should be your, like, breaking down the components of this formula. Does anyone have questions on how to use this, or do you want to go straight into the problems? Okay, can I clear the board? Yeah. Yeah. Can I get like thumbs up if you're okay with moving on?
Yeah, that's fine.
Pardon?
Oh, I mean, it's fine to move on.
It's fine with me? Okay, cool. So let me go ahead and clear it. Oh, okay. So this is our first problem. So the specific capacity of water is 4.184 joules per gram degree Celsius. How much heat is required to raise the temperature of 45 grams of water from 25 degrees Celsius to 40 degrees Celsius? I included the formula already here. So what are we solving for? Which variable? The Q, M, C, or delta T? We got one C, one Q. Any other?
I think we're looking for heat, which is Q in joules.
Okay, in joules. Okay, so yeah, that's correct. So the specific heat is this one already. So that's C. So we can plug that in here. 4.184 joules per degrees. Okay. So what other things do we have? What can we plug in? What else?
You can find out the delta T by doing 40 minus 25.
Yeah, perfect. 40 degrees Celsius minus 25 degrees Celsius. Okay. And then one last final thing that we need.
Oh, we can do M, right, for 45 Gs.
45. Okay. So before we move on, is everything in the correct units?
It looks like it because you could cross out like the grams and you cross out the C because both grams and Celsius are at the bottom. So you'll end up with joules.
Yeah. So we most often want to match it with the specific heat units. So this can be rewritten if we're just looking at the units. So grams, joules, grams degrees Celsius, and then degrees Celsius, right? And these would be on the top, right? Because there's nothing under it. So what she was saying, so she said that we could cross these out. So we got rid of the grams, we got rid of the C's, and we're left with joules only, which is the correct unit we want. So that's how we know everything's in the correct units. So let's say if this was kilograms of water, what would we have to do before solving it through? So if instead of 45 grams, if this problem was written as 45 kilograms, everything else is the same. It's just that they gave us the mass in kilograms. What would we have to do? Yeah, perfect. Yeah, we would have to convert it into grams, and that is the correct conversion factor. So yeah, okay. But luckily this problem is given to us in the correct correct units, sorry. So can anyone plug this into their calculator and let me know what they get? Okay, do we agree with Vivian's answer? Did anyone get the same one? So someone had mentioned sig figs. Okay, so let's talk about that. So what's given to us here, okay, for specific heat, it's constant. It's like it's always, it's like exact. So we don't count that when we consider sig figs, determining the sig figs. So if you recall back to the addition and subtraction sig fig rule, how many sig figs would be in this answer, just for temperature? 3, yeah, 3. It would be 3 because they have the same decimal spot, right? Not because there's 3 sig figs in each, but because it's the least decimal spots for a. So this is 3, right? So this is 3 sig figs. Sorry. Okay, so this one doesn't count, and then this is the only other thing that we need to consider. So how many sig figs are in this one? Are in grams? Yeah, 3 as well. So if our answer was or is 2821.5 joules, and we needed to make it into 3 sig figs, what would this be? Okay, yeah, 2820. Okay, so we figure out how many spots we need. So we need 3. We look at this number and the number behind it. If this is less than 5, so anything from 0 to 4, we make this stay at 2. And if it's anything above 5, so 5 to 9, we would have to change it to 2830. If this was like 2829, then it would be this. But since this is a 1, it'll just be 2820. Any questions on how we got this answer? Any part of the problem? No? Okay, I'm gonna go ahead and clear the board. We can move on to the next one. Okay, so we got the right answer. Okay. Okay, so let's have you guys do this one on your own. I'll give you guys about a couple minutes to do it, and then we'll discuss the answer. Yeah, if you have any questions, just let me know. Okay, I'll give you guys like maybe 30 more seconds to finish up your answers. Okay, so let's set up the equation. So it's kind of the same format as the previous one. So what would our formula look like? What variable are we trying to find? Q. Yeah, okay, perfect. Q. Same as last time, Q. Okay. And then what values can we plug in? Okay, thank you. 18 grams per mass. Okay. So what's our specific heat? Mhm. 4.184. Same units. Okay. And then our delta T would be 98. Yeah. Oh, I keep doing that. Okay. 98 degrees Celsius minus 78 degrees Celsius. Same. Do we have the same number of sig figs as last time? Yes. Yeah. Perfect. Okay. So are all the units correct before we move on? Yes. Okay. Perfect. So does anyone have any questions on how we got the formula? No? Okay, cool. So does anyone want to share their answer in the chat or out loud? Okay, got 1510 joules. Does anyone get, okay, we got 2. Okay. Does everyone agree?
I originally got 1,506 without the sig fig application.
Mhm.
Yeah.
Okay. Okay, cool. So it seems like we reached the consensus. Okay, so let us go and see what the answer is. Okay. Oh. Okay, go back. So what did we forget? Look at closely at the problem. Like, what is it asking? Because she will kind of make like not that she's trying to trick you or anything, but like you do have to be, yeah, Julia. Yeah. So it's asking for it in kilojoules. Mm-hmm. Oh, oops. Go back. Yeah, in kilojoules. Sorry. No, okay. Why is it doing that? Oh, oops. Sorry, that's my bad. That's my bad. It doesn't say kilojoules. Sorry, you guys are good. I'm so sorry. I guess I forgot to change that. But yeah, if it did say kilojoules, yeah, you would divide it by 1,000. I'm so sorry about that. That is my bad. But yeah, thank you for giving us the correct unit conversion. But yeah, okay, so sorry about that. That is actually my bad. Okay. What's going on? Okay, here we go. Here's the last specific heat problem that we will go over. This one's a little bit different. So it's saying the specific heat capacity of water is 4.184 joules per grams degree Celsius. That's the same. 2,800 joules is released to raise the temperature of a certain amount of water from 15 degrees Celsius to 32 degrees Celsius. how many kilograms of water was there? Okay, so let's kind of think about what it's asking us and what it's given to us. Okay, so which variable are we trying to solve for? M. Yeah, okay, M. M in kilograms. So we will convert later after we solve everything. So since we're trying to solve for M, what is our Q? Yeah, 2,800 joules released. Okay, so Q, we don't know what M is. The specific heat is the same. And then our delta T, be 32 degrees Celsius minus 15 degrees Celsius. Does everyone see where we got all the information and plugged it in? Any questions on how we set up the problem? No? Okay. So what is 32 degrees Celsius minus 15 degrees Celsius? Just this part. What does that equal? 17? Okay. 17.0, right? For sig figs. Okay. And then this drops down. M is still here. Here. Okay. So we would have to divide, right? Divide these two numbers multiplied, right? Right here. So what is 4.184 times 17? What's the product? Okay, 71.128. Okay, so what does that leave or what do we end up with a mass? Okay, 39. Okay, so I'm gonna do 39.4 grams. Okay, and then we're gonna go back to the problem to see what units we have to do it in, right? So, sorry. So 39.4 grams. What's the conversion factor again for this? For grams to kilograms. How many grams goes into 1 kilogram?
It would be 1,000 grams at the bottom and then 1 kilogram at the top.
Yeah, perfect. Okay. So like every unit conversion, if it's on the bottom, we divide. If it's on the top, we multiply. So since it's on the bottom, we would have 39.4 divided by 1,000, which equals our final answer. And can anyone give me the final answer? Thank you. Yep, perfect. Okay, cool. So I'm gonna give you like 5 seconds to kind of maybe write down some last minute things before I erase it and move on. Anyone have any questions on this one? Because this one's maybe a little more difficult than the ones that we went over. But for every specific key problem she gives you, she only takes away one variable. So as long as you know how to solve for one variable and you know where everything goes, then you should be fine for the specific heat problems. And that's why it's so important to know which unit goes with which, with the Q and the M, so you know where everything goes. But yeah, if no one has any questions, I think this is it for specific heat. But if something comes up, you can always ask me later at the end of the workshop. So yep, this is the answer. And if you're wondering why it's in 2 sig figs, it's because this is the same, oops. This is the same, right? So that 3, this one doesn't count. We don't know what this one is, but the given for this one, how many sig figs is that? Only 2, right? Yeah, it's only 2 because there's no decimal spot here. So that's why we would kind of cut the answer to only 0.039. Okay, cool. Let's go on to redox reactions. And I'm pretty sure she had gone over the acronym oil rig. So just as a refresher, can someone tell me what oxidation is? Do you remember? Oxidation is, wait, is losing electrons? Yeah, okay, perfect. Oxidation is the loss of electrons. And this E negative is just electrons. And then so that means reduction is the opposite, right? Because they're always paired together. There can't be oxidation without reduction. So reduction is gain of electron. So what does this produce? A positive or a negative? A more positive or a more negative atom if you lose one? Okay, so we have a split. Okay, so remember how electrons are negative? So if you lose a negative electron, it will become more positive. And I want to be careful with saying just positive because it can be something like Fe. Wait, not Fe. Well, yeah, we can do Fe. Fe 3 plus. Fe 2 plus. Okay. So if we went to go this way, did it gain an electron or did it lose an electron? Fe3 plus to Fe2 plus. Yeah, it gained an electron. So that would be reduction. So although it would be reduction, it's not necessarily a negative numerical value, but it is more negative. Does that make sense? Yes, okay, cool. So now that we have like the concept, does anyone have any questions about the concept of oxidation reduction? No? Okay. So okay, so our first practice problem, this reaction, so tin, I know that it looks weird because I couldn't find that, but this is basically what it looks like. So that's this. SN Q plus 4. So did oxidation, this is like the half ones. So I know I said that everything comes in pairs, but this isn't like a whole reaction. I'm not sure if you guys remember, but she also had like half reactions for these ones. So that's why it's only one or the other. But if this this tin is in its elemental form, so it has the net charge of what? What's the charge of just Sn? Any guesses? Okay, so let me give you a hint. So remember how the law of conservation of matter, or energy, or anything, it can't be created or lost within the chemical reaction. So if we look at the product side, it'll help us determine what happened on this side, right? Yeah, it's 0. Okay, so there's a 4 plus, and it also has a 4 negative, because remember electrons are negative. So this would be a net charge of 0. If you see anything with in its elemental form, so like what elemental form just means it's by itself, it's not an ion. So let's say Ca. Ca would just have a net charge of 0, which is different from like Ca, like calcium, the ion. So yeah, anytime you see it by itself with no indication of a charge, just assume it's 0. But yeah, so since this is a charge of 0 and it became a positive 4, what does that mean happened? Did it get oxidized or reduced? Yeah, oxidized. Yeah, perfect. So it became more positive because it lost an electron, right? Oil rig. And then this is just the indication of, hey, there's there's an excess of 4 electrons because we can't just get rid of it. So whenever you see a half reaction problem and the 4E negative is on the product side, it means it's oxidation. And on the flip side, if it's like, if the reactant side has like a plus something E, then it's reduction. That's like the shorthand way to do these problems. Any questions on how we solve this problem? No? Okay, cool. So let's, oh, yep, got it right. Okay, so let's do one with an actual reaction, whole one. So we're gonna figure out which one is being oxidized. So this MgS plus O2, which is a gas, makes magnesium oxide. So does anyone, what type of compound is this? Ionic, covalent? Ionic or covalent? Is it going to ionic? Yeah. And ionic means that there's a charge, right? So since there's no like plus or minus or anything, it's because it's can be assumed because it's an ionic compound. So this would be Mg. What's the charge for Mg? Yeah, plus 2, and then the oxygen is a minus 2. Okay, so breaking them down into the half type of reaction, so Mgs would turn into Mg2 plus 2, right? And since this is in its elemental form by itself, what does that mean that this charges again? Yeah, perfect, 0. So if this went from 0 to a plus 2, is that oxidation or reduction? Oxidation. Okay, so this magnesium is oxidizing. That has to mean that oxygen is reducing. It's being reduced, right? Any questions on this?
Did you find out the the charges for? So can you quickly go over how you found out the charges for NGO?
The charges?
Yeah.
Okay, so let me pull up my periodic table real quick to show you guys the charges. Give me 1 second. Okay, so let me. Okay, so everyone see the periodic table? Here, let me zoom in real quick. Can everyone see the periodic table? Yeah? Okay. So when you look at the periodic table, you can use this trick for the representative group only. So that just means that these rules don't apply to the transition metals and the intertransition metals. So this 1A group has a +1 charge. 2A has a +2 charge. Let me move this real quick. Skipping all the way to 3A, it's a +3 charge. This one we kind of skip because it could be a plus or -4 depending, but you don't really have to worry about that in the class because she doesn't use it. So we're gonna like do the anions. So this would be a -3, so it kind of flips. So this one's a -2 and this is a -1. This one doesn't have any because if you recall, the noble gas group it fulfills the octet rules, so they're happy. They don't really like to bond with other things because they're already at equilibrium. Does that kind of help answer your where did the charges come from question?
Yeah, so like you just like looked at the periodic table and like if I know that they're like the same, but if it was like if if it was like Mg like C, or no, that doesn't work. Or N, like would you like switch them? Like switch the numbers?
Yeah, so if we did Mg and N, so since this has a +2 and this has a -3, you would do the cross method. So you would put this 3 down here, put this 2 on the nitrogen. So this would have a net, or this would, because the goal is to have them have a net charge of 0, right?
Mm-hmm.
So there would be 3, and then this would have 2. So +6 and then -6.
So would the charge be +2, -3? Like would it be according to the periodic table?
Yes.
Okay. Thank you.
No problem. Let me go back. And sorry. Go. Okay. Okay, so we have another problem here. So which one is oxidized and which one is reduced? So breaking it down again, we have Al with a what charge? Just the normal Al. 0, 0 charge. Okay, and that would be an Al of something charge. So we have to figure out what the Al something charge is. Do you guys need the periodic table? Or do you have one with you? I could pull it up if you need it.
It would be +3, right? For aluminum.
Yeah, it's a +3 because it's in the 3A column, right? And then this one is a -1, but there's 3 of them. So there's 3. So if you can't remember what Al is, and you do know what Br is, you can kind of work backwards. If you know that this is a -1 and there's 3, you can figure out what that is, which is helpful for things with variable charges. So let's say you have FeO. Okay, so what is the charge of, okay, wait, let me backtrack. So if you can recall that iron has a variable charge, so it could be a +1, a +2, a +3. We don't know which one yet, right? But we can use the anion to figure out what charge Fe is. So thinking back to the last problem, what charge was O? Oxygen. Yeah, so -2. So what does that mean this is? What charge iron is? Yeah, it's a +2. So if this was an Fe, oops. Fe. Wait, oops, sorry. Let me go back. Okay, let me go back. Okay, so when we name it, right? When we name it, that's not what I want to do. So when we name it like iron oxide, right? Is that the correct name for that? Forgot. You guys also have to do this too. Is that correct? We named. Iron 2. Yeah, perfect. Iron 2. Yeah. So for when she asks you to have to name the ionic compound, she will most likely have one that's like you know how it's multiple choice. They'll have an iron 2, iron 1, iron 3, and then just iron oxide. If you don't include this Roman numeral, then it's wrong. So make sure you include that in when you're naming it. But yeah, I think that's all I wanted to add to this slide. Anyone have any questions for that? No, this isn't part of that.
When do you put the Roman numerals again?
If it has a variable charge. So you know how we looked at the periodic table and we kind of crossed out like the inner or the transition metals, like the middle of the periodic table? Because you know how the rule only applied to 1A, 1 or 2A, 3A, like we skipped that big chunk in the middle.
Mhm.
Yeah, that's a good indicator that it has like a variable charge because
Okay.
it doesn't apply to it. Yeah.
Thank you.
Yeah, no problem. Okay, so going back to the original problem of which one's oxidized and which one's reduced. This one is a +3. So 0 to a +3. Is that oxidation or reduction? Oxidation, yeah, again, oxidation. Okay, cool. So if aluminum is being oxidized, that means Br is being reduced. So yeah, I think that's everything for that one. Any questions? No? Okay, let me know. Okay, this is the answer. Okay, percent yield. Okay, this one's gonna be a pretty long problem. So when 5 grams of nitrogen and 5 grams of hydrogen are mixed, the reaction produces 4.02 grams of NH3. What is the percent yield? And I gave you the chemical equation. Does anyone know the percent yield formula? Percent yield. Yeah, so we have the actual over the theoretical times 100%. Perfect. So when it says the reaction produces 4.02 grams, is that actual or theoretical? Actual, yeah. So they probably did an experiment and this is what they got. Theoretical is always calculated and it's derived from the chemical equation itself. So before we can actually plug everything in, we have to figure out what the theoretical yield is. But before we have to find the theoretical yield, we have to find which one out of this N2 and H2, which one is the limiting reagent or reactant. Okay, so going to erase this. Anyone know where to start? What's the first step of solving for a limiting reactant? Change grams and mole. Yeah, we do. Okay, so we have 5 grams of N2. And then we have 5, oops, can't really see that. So 5 grams of H2. So we'll have to do 2 different processes, right? So we'll focus on the N2 first. So we have grams on the bottom, right? Moles of N2 on the top. So how many grams is an N2? 28. So we have 28. So actually, so after we convert it into moles of N2, the next step we have to do is to figure out how many moles of NH3 is, because that's what we're interested in, right? We're interested in the product. So in order to do that, we have to use mole to mole factors. So we bring down this N2, mole of N2, and we look at the coefficient. There's nothing here, but that means we can assume that there's 1 mole. And then the other thing that the one that we're interested in is turning into NH3, right? So how many moles of NH3 are there in this reaction? 2. Yeah, perfect. So after we cross out the grams, we're left with moles, right? Moles of N2. Sorry, moles of N2. Then we got rid of the moles of N2, and now we're in the moles of NH3. So we're almost there. There's one more we have to do, right? So there's a hint that it gives you what we would need it to be in, which is in grams, right? So we bring down that moles of NH3, and there's only 1 because we're just figuring out the molar mass. So remember, the molar mass, the unit is grams per mole. So that's what we're using. So what is the molar mass of NH3? Okay, so you have 17. Okay, cool. So going through everything, sorry, let's cross this out. Going through everything, we finally end up with grams of NH3, sorry. I don't think we'll have space for that. So going back on the problem, we would have to do 5 divided by 28 times 2 here, and then times 17, right? 5 divided by 28 times 2 times 17 is
Like 6.07.
6.07 grams of NH3. And someone had asked if to compare which is the limiting reagent or reactant is. You can compare the number of moles, because it'll still give you an indicator of which one produces more. But I would recommend going the next step of finding the grams of NH3, because you're going to use that anyways for the percent yield. Does that make sense? Yeah, okay, cool. So we're just gonna put here 6.07 grams of NH3. And then I'm gonna clear this. And then we'll do the same exact thing for the other value that was given to us. So we have 5 grams of H2. Okay. So again, what's the first conversion factor we have to use for H2? To moles, yeah, okay. So we have 2 grams, 1 mole, H2. Okay. So we got rid of this. We're on to what? What next? What are we converting this into next? So we bring this down, 1 mole of H2. What are we into? Okay, yeah, 2 moles of NH3. Oh wait, sorry, not 1 mole. 3 moles. Here you go, 3 moles because of that coefficient. So 2 moles of NH3. Perfect. Okay, so we got rid of this, moles of H2. Next thing we have to do is what? What's on the top? What are we looking for? Yep, 17 grams of NH3. We should be at our desired unit. Okay, so 5 divided by 2 times 2 divided by 3, and then times 17. What does that get us? Point 28.33 grams of NH3. So which one is N2 our limiting reactant or H2? Yeah, N2. So limiting reactant is the smaller value, right? Because if we had 5 grams of H2 and we don't care about this part, we would produce so much more, right? We would produce so much more. So this is the amount of N2 is what is stopping us from producing even more. So since we already solved for the grams of NH3, this is our theoretical. So theoretical, we are now able to already move on to the percent yield formula. Going back to percent yield equals actual, right? Actual is our 4.02 grams NH3 over our theoretical, which we already solved for, 6 grams of NH3 times 100%. What does that get us? $66. Okay, cool. So any questions? Any questions on this? Because I know it was a pretty long process. No? Okay, I'm going to clear. Then we will go to the next one. Okay, so this one is if 4.5 grams of potassium are mixed with excess Br2 in the reaction that is given, what is the percent yield when 0.110 mole of product is actually collected? So going back to a student who asked earlier if we were supposed to compare the moles or the grams. it just depends on what the product or the problem's giving you. So since this is giving us moles, the number of moles, we can convert that into grams. And it only says product because there's only one product. So this doesn't really, this problem already indicates that this is the limiting, the limiting reagent or reactant. So we don't have to solve for that one because it says excess. So this means that this is the LR, right? So the only thing we have to do is, what do we do with this 4.5? Or actually, you can go both ways. You could either convert this into moles, or you can convert this into grams. But I would prefer doing it the other way, where we convert this into grams. So still two steps of 0. Or I guess we could do the other way. We could do the other way. So 4.50 grams, just so you can see both ways. So 4.5 grams of potassium. So what do we convert that into? Sorry. What do we convert that into? Because it's not the product, right? It's not KBr. So we have to convert it all the way to moles of KBr. Yeah, but yeah, exactly, Vivian. So we have to convert this first into moles. So we have 39 grams of K per 1 mole of K. Okay, so after getting rid of that, then we can go to what? What next? This is 1 mole, okay? Or actually, it's not 1 mole. Mole of K, right? 2 moles of K because of this coefficient. What goes on the top? What are we interested in? Close. 2 moles of KBr because of this coefficient. But yeah, so after we get rid of these moles of K, we are left with the moles of KBr. If this didn't give us, like if this gave us an amount of Br and we had to find the limiting reactant, we could stop here and figure out which amount of moles is less, right? But since this has already given us that there's only one amount that we need, this is the theoretical value, right? So what is the product of this? This divided by that, by 39, and this becomes a 1, so it's really just 4.5 divided by 39. Anyone have an answer for that? Okay, 0.115. Okay, so that's pretty close to our actual, right? So when we plug it in our actual versus, or our actual one, 0.110 moles KBr theoretical we had found is KBR times 100. What is that percent? Mm-hmm. 95.7. Perfect. Okay, so as you can see, yes, you will. You have to do the survey and then put in your email in the survey for me to be able to send you a PDF copy of the slides. Mhm. So yeah, so as you can see, the previous one we used grams of the product, but this one we're using moles of moles. So you can use either or, it's as long as they're consistent, you know, like you can't have this as grams. As long as they're the same, then it should have the same ratio. But yeah, any questions about this one?
So is the answer 95 or like 95.7?
Mhm.
Okay.
Cool. Okay, so we are going over molarity now. So just a refresher, molarity equals M of solute and L of solution. So what does this M mean? Because it's different from the M from the specific heat. What does M mean? It's actually mole. It's mole. I don't know why your textbook said that, but it's moles of solution or moles of solute over liters of solution. So mole over liters. Okay. Okay. This. Here. Just so you don't get confused. What is the molarity of a 0.650 liter solution that contains 78 grams of KCl? And I already gave you the molecular weight of KCl, which is here. Okay, so how do we set this up? What do we already have?
We have liters, we have grams of KCl, and we have the molecular weight.
Okay, perfect. So because we want this in moles, and this is given to us in grams, right? KCl, we can convert this into moles, which is 74.55 grams per 1 mole. So what does that become?
I got 1.046.
1.046, okay, moles, okay. And then we can go into the actual molarity formula, 1.046 moles over liters of solution, which is already in liters. So what is the molarity? Anyone?
1.609.
Okay, so 1.6. Well, 1.609 is correct. It's just remember to apply the sig fig rules looking here, we have, we base it off what's given to, oops, sorry, what's given to us, right? So this is 3 sig figs. However, this is 2, right? And the only thing that we use is multiplication and division sig fig rules, right? Because there's no addition or subtraction. So we would have to use 2 sig figs. But you got the right answer. So yeah. Okay, and I think we're almost done. Almost done. We have 15 more minutes. Okay, so I use the same solution, or well, kind of the same KCl. So the solution has a molarity of 1.20 m. 1.20 m. How many grams does a 798 milliliter KCl solution contain? And then we also have the molecular weight if we need it. What can we plug in to our formula or equation? Say. What value is also given to us besides the molarity? We use this one. What's the other number? Yeah, thank you. 798 milliliters, but we can't quite plug it in yet, right? So we have to convert it. Yeah, thank you. Milliliters, 1 liter, that's a conversion factor. Vivian already gave it to us. Okay, so, and we're solving for X, which is moles of solute. Okay, so what is the moles that we end up with? So 1.2 times 0.798. Zero 0.9576 moles of KCl, and it's asking us grams. So always be careful of what they're asking you. So 1 mole of KCl is 74.55 grams. So that should give us our answer. And I'm gonna just go ahead and show you what the answer is. You can check your answer to see if you got it correct. Yep, 71.4. Okay, cool. So moving on, just because we're getting close to the end, I think this is our last one. Okay, so dilution formula. So C1 V1 equals C2 V2. What does that concentration mean? What is the unit that we're using for concentration? Yeah, molarity. Yeah. So it could also be rewritten as M1 V1 equals, oops, sorry, M2 V2. Same thing. For dilution problems, it doesn't matter if your volume is milliliters or liters. It should have the same ratio, as long as they're, oops, you can't see that. As long as they're the same on both sides. right? So just be consistent with your units and you should have the same or the right answer. But molarity is just, there's only one. So that, okay. So our first problem is, what is the molarity of a solution prepared by diluting 12 milliliters of a 2.7 molarity NaOH solution to a 70 milliliter NaOH solution? I know that was a lot, but it's a lot simpler than it seems. Okay, so a good indicator of what is together is the word of, right? Of. So that means that this is one side of the equation. So we can put in 12 milliliters and the 2.7 liters, or sorry, not liters, molarity. Okay, and then we trying to find this molarity, and this is given to us. Okay, so what do we end up with? What is the molarity of the final, or of the diluted solution? So what's 2.7 times 12 divided by 70?
I got, oh wait, actually never mind. Sorry, I did the math wrong.
Okay. A person got 0.46. Let's check and see if it's right. 0.463. Which actually is wrong. You're actually right. Sorry. So this is 2. So
Are you able to put the work back up?
the work, yeah.
Thank you.
Let me. There you go. You see it better. Oops. Keep actually clicking it. 0.46. Is the correct answer. Let me know when you're good to go.
I'm good.
You're good? Okay, cool. So almost done. We're almost done. Okay, so what's the molarity of a solution prepared by diluting 0.012 liters of a 2.7 molarity HCl solution to a 340 milliliter HCl solution? So same thing here. Do we want to use liters or milliliters? Up to you guys. Doesn't matter. Liters, milliliters.
Molarity is moles over liters, right? So
Mhm.
we should be using liters, or what they gave us. Oh, but we would have to convert 340 milliliters.
Yeah. So for, like I said earlier, the V's can be in liters or milliliters, as long as you're consistent with both of them. But yeah, you're right. We have to convert this milliliters, right? There's that. Okay, so after we convert it, we can plug it in. Oops, 0, 1, 2 liters. 2.7 30 equals 32. And this should be 0.3. I'm pretty sure. Okay, so what did everyone get for this second molarity? Okay, 0.5 okay, cool. Usually when like a definite indicator that you will use this equation is if it straight up says diluting or dilution, then that is the only time you use this equation because it's very specific. Any questions on this? Question? No? Okay, I'm gonna go ahead and clear the board. Okay, and that's it. We're done. I think we have like 5 minutes left for extra questions you may have. You can stay after even more if you have more questions, but other than that, you're free to go. I'm gonna go ahead and send in the survey link and the YouTube link once again, just because I don't want you guys to scroll all the way back up. Oh, sorry. Sorry. I don't want to make you guys scroll all the way up to all that to the beginning of the chat or the middle of the chat or whatever. But yeah, anything else? Any questions? You can chat to me or unmute yourself if that's easier. But other than that, I wish you guys good luck on your finals. And yeah, bye.
Thank you.
You're welcome. A student is asking, how can you tell which one is the C1 or C1V1 or the C2V2 in the problem? Okay, so C1V1 is the initial, like the normal one, and then the C2V2 is the diluted one. It honestly doesn't matter which one is which, as long as you have the right numbers grouped together. And I'm just gonna go ahead and use this one as reference. And that's why I kind of told you guys about that like powerful like 2-letter word of, and that indicates that they connect together. So you can tell by the sentence structure, right, that this is the C1V1 because it's asking what is the molarity of the solution prepared by diluting it, right? Diluting this one. So since we're diluting it, that would be this C1V1. Does that make sense? Yeah, okay, cool. Any other questions? And it doesn't have to be directly about this one or about anything like just like last minute, because I know that your guys' final is pretty soon. Doesn't have to be about the topics here. Okay, so if no one else has any questions, I'm gonna go ahead and end the workshop here. Thank you guys so much for being so great. Yeah, I'm glad. Thank you. Thank you for participating. Thank you for coming. Yeah.
Thank you.
You're welcome. Bye. Have a good day.